Hello, and welcome to our second Spud Smart webinar of 2017. Today we'll be looking at water management in potatoes. My name's Janet Canters. I'm the editor of Spud Smart magazine and spudsmart.com, and today I'll be serving as your moderator. First, I'd like to thank our sponsors, McCain Foods and BASF, for their support. I'd also like to note a few housekeeping items for today. So the webinar is being recorded and it will be made available on spudsmart.com following the event. For audio quality purposes, all microphones have been muted with the exception of speakers. We do welcome your input, so if you do have a question or comment, just share it in the chat box at the bottom on the bottom left side of your screen and let us know who it's directed to. So today we have two speakers who will talk about water management in potatoes. We have Mary Lemaire, who's Manager Agronomy Midwest with McCain Foods, and Ted Harms, Soil and Water Specialist with the Irrigation Management section of Alberta Agriculture and Forestry. Today we'll start with Mary, who will talk about potato defects and disorders with too much water and too little water. And then we'll hear from Ted, who will share information about soil moisture monitoring and making irrigation decisions, and about the pros and cons of soil water sensors. So we're ready to go with our first speaker, Mary Lemaire. Mary, the floor is yours.
Thank you, Janet. So as Janet introduced, I'm going to be speaking for a few minutes about some potato disorders that we see related to water management. So when it comes to water management in potatoes, we're trying to hit a rather narrow target. The idea, of course, is to optimize yield and quality of the crop. This graph is from work done in Idaho, and you can see that the optimum irrigation is a very narrow range, and it's very easy to either over-apply or under-apply our irrigation water. Excess moisture at planting promotes seed piece decay and can delay emergence. In the photo on the left, you can see standing water has prevented emergence in the field. And on the upper right is a seed piece that has started to decay after it has already sprouted. Soils that are waterlogged for a period of a few days can lead to these situations with either no emergence or very delayed emergence. Brown center is a discoloration of the pith at the center of the tuber, and that's the photo on the left. This can be induced when available soil moisture is above 80 to 85%, so again, in excessive moisture situations. The brown discoloration that you see at the center of the tuber results from the rupture of cell membranes and death of the surrounding affected cells. Tubers are most susceptible to this disorder when tuber initiation occurs or through early tuber bulking. And brown center is actually considered a milder form or a precursor to hollow heart, which is the picture on the right that I'm sure many of us are familiar with. Hollow heart is most often associated with brown center and tends to occur during the latter part of tuber bulking. It's caused by a growth stoppage, whether due to water or nutrient stress, followed by a return of favorable conditions that cause rapid tuber expansion. Black heart occurs in the field, and I've also seen it in storage, when oxygen supply to tubers is insufficient to support adequate respiration rates. The disorder can be found in waterlogged soils and low-lying areas that remain saturated for long periods of time, and basically it creates anaerobic conditions and the tuber can't breathe properly. If these anaerobic conditions occur right after planting, it can lead to full seed piece decay and spotty emergence. In cases where waterlogged conditions happen and you have a seed piece that's trying to sprout and emerge, sometimes you can't even identify that it's the black heart that is the problem because the seed piece will physically rot away. The last disorder I want to talk about related to excess moisture is swollen lenticels, and I'm sure many of us have seen this. Lenticels are the opening on the potato that allow for air exchange, and they tend to become enlarged when exposed to either waterlogged soils or prolonged wet conditions. Swollen lenticels make the tuber more susceptible to entry of disease organisms like soft rot because it's basically an opening in the surface of the skin. Heavy rains during harvest can be of particular concern because of the risk of development for storage diseases. Allowing soil moisture to drop between 65 to 70% between irrigation is usually adequate to prevent swollen lenticels near the end of the season towards harvest. So now we've discussed a few things that happen under excess moisture conditions. Let's review what can happen in moisture deficits. First, I'd like to talk about the impact of canopy temperature, and that means talking about the stomata on leaves. And stomata are tiny openings or pores on the surface of a leaf that are used for gas exchange. And water deficits cause the stomata to close, and that leads to an increase in canopy temperature and reduces the ability of the leaves to produce an evaporative cooling effect. So this kind of causes a cascade effect which slows down the rate of photosynthesis and leads to decreased production of starches and sugars in the plant. If you have less starch and sugars in the plant, that means you're also getting less starch and sugar being translocated into the tubers themselves. So tuber growth will also be reduced, and that of course impacts overall yield. So this chart shows the impact of soil moisture and soil temperature at tuberization on yield, specific gravity, and sugar ends. This data is from a study done in Idaho, so I am presenting someone else's data here. Generally, sugar ends are more common in years with hot temperatures or in fields that experience moisture deficits during the growing season. So this Idaho study used 4 treatments. The control for this study, the first one listed, used ambient temperatures under normal moisture conditions. And in this study, when they say high moisture, they mean normal moisture. The second treatment on the list in the chart includes a water deficit or low soil moisture, meaning the available soil moisture was allowed to fall below 50% between irrigation events. The third treatment, again listed as high soil moisture, means normal, and then high soil temperatures, where the researchers placed heat cables in the soil to raise the temperature 10 degrees Fahrenheit above the control temperature. And the final treatment listed was a combination of low soil moisture along with those high soil temperatures. And you can see on this chart, or this table, that the greatest impact on yield of US #1 tubers and development of sugar ends was in that very last one, the dry, hot conditions. However, looking at the second treatment with just the dry conditions alone, you'll see that resulted in a 16% reduction in US #1 yields alone. So moisture deficits impact US #1 yields. And we talked about disrupting the starch accumulation process and translocation of starch and sugars into the tubers. Disruptions in this process, particularly during tuber bulking, can lead to malformations such as pointed ends, dumbbells, bottlenecks, and knobs. And of course, as we know, having a high amount of misshapen tubers means that they're graded as non-US #1 yields, meaning the more misshapen tubers you have, the lower your US #1 yields are going to be. And like the picture on the left, which is a tuber with a pointed stem end, having a pointed stem end indicates that the stress the tuber was under happened early in the season. While if the tuber shows a pointed bud end, that's the result of a stress-induced restriction that occurred during late tuber bulking. Dumbbell shapes like the photo on the right are caused by growth interruptions midway through the bulking season. And with russet Burbank, moisture stress during tuber initiation particularly can result in reduced US #1 yields anywhere from 10 to 40%. So sugar ends, if you work with processed russets, you are familiar with sugar ends. Sugar ends are typically associated with periods of high air and soil temperatures, along with water deficits, particularly during tuber initiation and early bulking. Sugar ends show up as a post-fry darkening on one end of the French fry. It can happen on either the stem or the bud end. Picture here obviously shows it on the stem end. It's primarily caused by an accumulation of reducing sugars at that particular tip of the potato. Often the end of the tuber that fries dark also exhibits a restriction in growth or a pointed end. So if you're seeing potatoes come into a facility or come out of your field and they have a pointed end, you should be aware that you might see sugar ends show up when they're processed. The darkened end will also often have a reduced specific gravity and a glassy, translucent appearance. In severe cases, this disorder predisposes the tuber to further tissue breakdown and development of what's called jelly end rot, which is what you can see in the picture on the left. Growth cracks in secondary tubers can also be caused by fluctuations in soil water availability, again, particularly during early tuber bulking. So knobs, which I'm sure most of you are also familiar with, as the picture on the left, are caused when secondary growth occurs at the lateral eyes on the tuber, and this signals that there was a loss of apical dominance in that tuber. Growth cracks, on the other hand, are often caused by irregularities overall in tuber growth. And those growth cracks are very, very common when there's fluctuating water supplies. Potato varieties vary in their susceptibility to all these different malformations that I've talked about. And prevention of these malformations is primarily accomplished by maintaining uniform, adequate soil moisture and nutrient levels through the tuber bulking period. And I want to spend just a few moments talking about a few varietal differences. Much of the information provided when discussing water management, particularly in processed potatoes, is aimed at russet burbanks. Varieties respond differently to environmental factors like irrigation and moisture management, and that response can, well, let's just say it varies widely. Varieties susceptible to stress-induced malformations such as Ranger russet will require high levels of soil moisture during tuber set and early bulking. Inadequate moisture during tuber initiation can result in really long, thin tubers in a Ranger russet. And prolonged deficits may induce those misshapen tubers or sugar end discolorations. Varieties susceptible to water rots, such as russet Norcota or Shepity, need different moisture management, and those varieties really need reduced moisture near the end of the growing season. So russet Norcota is known to have slightly smaller vines and less water demand later in the season compared to russet Burbank. It's known to require 20 to 30% less water in some cases, and over-irrigation of this variety can lead to pink rot and other storage issues. And finally, Shepity is also a water rot susceptible variety. It also tends to be susceptible to heat sprouts and heat-related reductions in specific gravity. So frequent light applications of irrigation can help reduce some of these issues. And available soil moisture during that late tuber bulking period, dropping to about, say, 60% available soil moisture between irrigation events, can help reduce problems with pink rot and pythium leak in Shepity. So now that we've reviewed a few potato disorders that are a result of excess or deficit moisture conditions, we can move on to Ted, who I understand is going to cover some details related specifically to irrigation management.
Thank you very much, Mary. If anyone has questions for Mary or Ted, please feel free to type them in the chat box, including whom they're directed to. So we'll try to make sure our presenters have a chance to answer them at the end of the presentation today. So now we'll move over to Ted Harms. Go ahead, Ted.
Okay, thanks, Janet. We'll just get going here. We'll talk a bit about soil water sensors for irrigation scheduling, the pros and cons of them, and then kind of the whole irrigation management component with them. So oftentimes people have come to me and said, why am I not getting my yields? I'm doing everything that maybe my neighbor might be doing in that. And oftentimes when we go out and look, we will find that it's just kind of an irrigation management issue. So I'm just going to show on this here. You can see that this one here is it's a wheat field, it's a pivot field, it's a section pivot. And he's going into the season after seeding with very low soil water. And he put on, with rainfall and irrigation, there's over 400 millimeters applied, but yet this is his what's called a management allowed depletion, and only very seldom during the season did he get there. So had he known his soil water status prior to the irrigation season, he could have done something at that time to start adding to his lower, like this lower level here for soil water. This one here, I said when informed where the soil water level is in the field. Here is again, this is a management allowed depletion, and this fellow here, we monitored the field actually, so here you see it's a center pivot the same, but it kind of kept the soil water within that zone where he wanted, and again, so he finished the season quite happy with his yields, and that this was a different field. So I put here, what's it costing me? This particular study here was an environmentally smart nitrogen study. One was done at a site remote to us. One was done within our location here. We monitored the irrigations for one site. The irrigations were kind of left to the operator at the other site. And it wasn't an irrigation study, it was an environmentally smart, a nitrogen study, yet the difference in marketable yield with regular soil monitoring I put was $1,000 a hectare. So what is it costing me with improper irrigation? Quite a bit actually. So I put here, why do you currently make, or how do you currently make irrigation decisions on when to irrigate? And here, just as Mary indicated, with your yield reduction, once your plants are under stress, here is a study showing that, once it's under stress, your plant starts to heat up a little bit. So I say, how do you currently make irrigation decisions? Hopefully not like this. You wait for the crop to show symptoms of stress. But quite surprisingly, this is a study done out of Washington State, and they surveyed numerous irrigators, and they said, what do you use to determine when to irrigate? And the number one way that irrigators use to determine when to irrigate is the condition of crop. Actually, it's when they see the stress or the feel of the soil or a personal calendar, those three. And to the right of this is kind of what I'm going to talk about today, what is not commonly used, but maybe it will stimulate a few people to start using that. And the reason that is because once this is just a yield versus evapotranspiration graph here, and all of them, whether it's potatoes, barley, canola, soybean, they're a straight line. So as long as your crop is allowed to transpire freely, then you're going to get your highest yield. But if that doesn't happen along the way, so it's moisture stress, then it can never attain that maximum yield. So here it's at 620. And again, if it incurs moisture stress again, then here we're down at 450. And that's the best that field can do. And so ensuring that that crop or the potato has sufficient soil water to transpire freely, then kind of starts getting to be where you would get your maximum yields from. So there has been a lot, and this is no surprise. There's people have done irrigation management. When I was a kid, we did it with shovels. This is just different step-on sampler, or what's called an Igelkamp sample, or a Dutch auger, and then you take a soil sample and you feel it, and you determine what your soil water is in that particular profile. Nothing wrong with that. It works for a lot of people. A lot of irrigators use it, have used it, still use it. But this is one where I say when a shovel or a step sampler don't fit anymore. And this one here it's a potato field we monitored, and you start seeing this, the blue on the bottom is your rainfalls, the green is your irrigations. And so you start seeing the frequency of irrigations that is required to keep that kind of into that management allowed depletion, where it's kind of between field capacity and management allowed depletion. And so here, if you're managing more than, a few fields, you can start seeing the limitation of your step-on sampler, because it's a major effort to try and get around to each of the field. And if you get behind, you lose in yields. So There's all kinds of different soil water sensors available now. I think at last count I counted 52 of them, but there's probably a lot more that I'm not familiar with. But how the heck can I use these things to help me make irrigation management decisions? So what's in the shopping bag for soil water monitoring? So there are ones that use kind of what's called the tension or the soil matrix potential. They're tensiometers, they're resistance sensors, watermark sensors and that, gypsum blocks. And how they work is that they have, they just measure the tension. So when there's a lot of water in your profile, your tension is less. As your soil dries, your tension goes up. And so these ones just monitor that. As the soil is drying, you just get a higher reading with your soil tension than when you have lots of water available in the profile. So that's how these ones work. How they're used, though, that's the problem. It says, when should I irrigate? Depends on the soil texture of the field. So it says, okay, I'm getting a soil tension reading of such and such. Does that mean that when should I irrigate? Well, I can't, nobody can tell you that unless you know the soil texture. So here is, we have sand, we have clay loam, we have a clay and a peat, and you see that at, let's say 100, this one is kilopascals, at 100 kilopascals, you can see that, oh, your sand is it's almost at wilting point. You should have irrigated a long time ago, way down here. Whereas your clay loam, you should irrigate, and your clays and your more organic soils, you have lots of water in. So how can I use these things? When should I irrigate? I can't tell you that unless you start knowing your soil texture. And your soil tension, or your soil that matrix forces, is related to your soil water. So these are called soil water characteristic curves or something like that. And you can get them, but you see they're different for a sandy loam versus a clay loam. So at different soil tensions, you have different, I'm just going to put this, at different soil water tensions, and this is in bar, you have differing amounts of soil, water available in your profile, and it's texture dependent. So how can I make irrigation decisions using these types of soil water sensors? Well, either you calibrate yourself and you say, like a kind of with a hand feel, you get a reading from your tensiometer or your watermark sensor, and you say, okay, now it's where I would normally irrigate. You take the reading, and so you kind of have to calibrate yourself based on the reading from your tensiometers or watermark or your gypsum blocks. Or if you can, they can do it. They do a soil water release curve for your different soil textures, and then you can get your values in volumetric water content percent or something that then you can relate to, as Mary had indicated, available soil water content. Other probes, there are lots of them. This is probably the biggest new probes that are coming out always use this type of property. It's just the dielectric permittivity of the soil, or dielectric constant. And the reason they work is that the dielectric constant of air is minimal. The dielectric constant of the mineral component is fairly constant, around 4 or so, in 2 to 5 in that range. But the dielectric constant of water is 81. So I think at the bottom, if something changes with the readings, with these probes, it's not, the air is minimal, the mineral component is static, so what changes is going to be your soil water content. So that's how they work, is measuring that type of property with the soils. And there's many different types. There's some with the time domain transmission, which is a standing wave interpretation. Time domain reflectrometry, they're TDR probes, they're called. They kind of measure a propagation velocity of a wave. And then again, it's just using that property. There's other people who have done a much better job of how these things work, but it's just measuring that property of the soil, that dielectric permittivity. So, and then they just relate that to your soil water content. There's capacitance sensors that, again, they might look familiar to some that are familiar with soil water sensors. and it just uses the soil to complete the capacitance circuit. And again, less or more gives you different readings. There's some, here's a frequency domain or impedance type probe, and again, they're using that property of the soil, that dielectric permittivity or dielectric constant. They're all good, but the trouble, I say, is the output for all of these is in volumetric water content %. So when somebody says, okay, well, I'm getting a reading of 19%, should I irrigate? Do I have lots of plant available water in the profile? Do I need to irrigate? And a reading of 19% volumetric water content means nothing. You can't make a decision with it unless you know your soil texture. So here I have it where I have 19%, and you see across the bottom that I have the different soil textures. And this unavailable water, it still has water in the profile, just the plants can't obtain it because it's held on too strongly to the soil components, the soil mineral components. So, but you see that difference between how much the maximum amount of water a soil profile can hold, provided it's freely drained, and when there's no available water in there, is soil texture dependent. So at 19% with your probe, with your sand, it wouldn't be able to hold it. You can never get to 19%. It would just drain through the profile. Sandy loam, similar type thing. You see, once you start getting into a loam soil, you're full. You're at field capacity. You're at the maximum amount that profile can hold. But if you go across to a clay loam and a clay, you should have irrigated a long time ago with a reading of 19%. So a reading of 19% volumetric water content % means nothing unless you know your bucket size. Oops, get rid of my pointer here. There we go. Unless you know your bucket size. So what's my bucket size for my soil? So every soil, depending on your soil texture, has a different amount of soil water that they can hold. So when you're talking about available water, and that's as you're making irrigation decisions, 60% as Mary indicated, or 90% or 70%, that's what you're talking about. What's my bucket size and how much has it been depleted? So how do I use data from these probes when it comes out in volumetric water content % to make irrigation decisions? Well, you have to do some calculations, and you can. You take a 23% volumetric water content, you do some calculations, you convert it into millimeters of water or inches of water, depending on your units, and then you can determine where your wilting point is, and at the end of all of your calculations, you can say that, okay, so I have 50%, all I've done is take 23% volumetric water content, and with my particular soil that I used, now I have 50% available, and so I know I should have probably been irrigating a while ago. So how much can my soil profile can I hold? Well, then again, you have to do all the calculations. So all of these probes, they will read out in volumetric water content %, but for you to be able to make decisions, irrigation decisions on what's the status and how much should I irrigate, you can't do that without doing subsequent calculations somewhere on your computer or something like this. This one here is real-time moisture monitoring, and this one is, again, they're being sold. There are a lot of consultants and different people use them. Nothing wrong with them. You can see it kind of, here's an irrigation, and you see how the plants are using the water, and then you get an irrigation. And you see up at the surface at 4 inches, it's much more dynamic than at 30 inches where you have no water use. Okay, now how can I use these things to make irrigation decisions? Well, here's a graph, and this, and most of these that I've seen and that I've used, you have, this is called a refill point, and this is called your full point. And you have to set those for a full and a refill point, again, depending on how your trace is working. So what I've done here is I've said, okay, this one here is an over-irrigation. So you can see how the plants are using water here, they're using water here, fairly consistently they're transpiring. But here you see it's a very peaked, a steep drop, and that means that your profile drained. And actually, you can see it down here where you get a little bump up at 20 inches. So your profile has drained through the 0 and 15 inches, and it's bumping up this. So that's what that's indicating. This is normal crop water use. And so I can set my full point right where I see that inflection, where it, it drops steeply and then it starts going like this. Okay, this is my full point. Okay, so I have that set. And then you say, okay, well, how about the refill point? Here again, you can see that on this graph that you have normal transpiration, normal transpiration, normal transpiration, but here you get an inflection point. And so here your crop can't transpire the way it should. It's struggling a bit. It's struggling to get that soil water. So as soon as right at that inflection point, then you put your refill point. So now I've got my full point, I've got my refill point, and now I can watch my trace throughout the season. So how do you use these probes to make irrigation decisions? Pretty tough if you don't know your full and refill points. So you have to kind of watch a trace of the soil over time, start setting a full and refill as you approach your refill point. It's time to irrigate. So that's how these ones. So what's the instrument of choice for monitoring soil water in irrigated fields? Well, in our area here in southern Alberta, 70% of irrigators in the Tabor area, this is a study done out of the University of Lethbridge, and 40% of irrigators in Raymond still use the manual sampler for checking soil water and scheduling irrigations. There are new ones coming out. There are some that are wireless soil water sensors and with wireless networks that have all of the components out in the field, and then they talk to transmitters, and they go to a central receiver, and this one is a hobo node network, and there's others as well that use wireless communications for that, so you can get a sense of where you're at in the field. Again, they're all reading out in volumetric water content %, and as I indicated earlier, that comes with its own issues. So what's the bottom line? There's many areas of the world, consultants are monitoring soil water on a continuous basis. Communication is via cellular, internet, satellite, or Wi-Fi. Irrigation decisions made on the information obtained, and usually, and there's many reported studies out of many states, Florida and that it improves irrigation efficiencies and usually improves yield. You get the maximum returns. Just like that yield ET curve, it's a straight line. So as long as your plants aren't limited by transpiration, then you should realize your maximum returns. The other thing I would say is that, just as Mary indicated with your Shepherdese, is that to dry down to 60%. How would you know 60% if you didn't monitor your soil water? Okay, so all of them work. They're nothing wrong with them. They all work within their limitations. They all have different technologies, and so being with different technologies, they all work. Some don't work as well with clay soils, some not so well with sandy soils, but they all work within their design specifications. They sample a very small soil volume, so just usually about 10 centimeters, a half an inch or so around that, or a half an inch, 10 inches or so. 10 inches? Where am I at? Maybe less. Yeah, no, probably about 4 inches or so around that volume. So the question is, how many of them should be placed in each field? Many require the purchase of expensive access tubes. So if you're doing depth monitoring with these probes, they need a very tight soil tube contact, and so with them, a lot of times they come with fairly specific installation equipment for them to work properly, so you don't get gaps along the tube soil interface. Most of them require soil-specific calibrations to improve accuracy, so you will get, maybe when you buy them, you will get a mineral soil, organic soil, or something like that. But when you're getting into your gradations of soil texture, like your loams and your clay loams and your sandy loams, then to improve the accuracy of them, oftentimes they require soil-specific calibration. And most require further calculation of output. So when it's in volumetric water content %, kilopascals, bars, or something like that, to convert it into a meaningful value of percent available soil, millimeters or inches of deficit, so you know when do I irrigate, where am I at, how much percent available is there, and how much should I be irrigating, then it requires that you need to somehow do further calculations, like on your office computer or your farm computer. So to convert kilopascal or bar to a meaningful value, then oftentimes you need a soil water release curve derived for you from a lab or something. So where are we? There are new sensors coming to the market that kind of do the calculations. They set the bucket size depending on what you put in for your soil texture. So they set the bucket size, and then your readout is in percent available. So this particular little thing I have at the bottom is it's not from a soil water sensor. It's actually from the irrigation scheduler from Troy Peters in Washington State. But the newer probes are coming out something like that, or and they've just started over the last few years. They're starting to set the bucket size for you, and then you can see then as your soil dries, you start knowing this is 50, 25, 0. So it's your readout with these new probes is in percent available, and then you can start seeing where you're at. So if you need to dry down to 60% of available for your Shepherd's, well, if you have a probe that reads out like this, or this is a particular irrigation app, but then you can use those for determining where you are at the field. So it sets your bucket size for you depending on your soil texture. Many of the new ones have apps that download to a smartphone, and so it just has a SIM card in the head of the probe, and so you can take a look at your smartphone and decide where your soil water is within the field, and it's on a real-time or near real-time basis. So a few of them, they're capacitance sensors. They measure the dielectric permittivity, no new technology. However, what's new is somebody's thought about how irrigation producers are going to use these probes. So this one here is a Ization out of the Netherlands. And it's color-coded as well, so you can see it's in the field, communicating via cellular. Output is on your smartphone, and it identifies where you're at within the field, and it gives you your deficits kind of in millimeters and that. Only criticism with it is it sets your bucket size for you, and if you don't like what it sets, and you said, well, no, my available soil water holding capacity is a little bit more than that, then rather than giving you the flexibility to set that a little bit larger, it tells you to change your soil texture to a different texture. And so that's the one thing I dislike about it. This one's a new one. It's not available in Canada yet. It's available in the States. This is from CropX, and it's kind of the same thing. Again, just on you see your output here is that it's color-coded, so you can kind of know where you're at. And it gives it, again, there's much more detail behind the scenes for percent availables and different things like that. So that's all coming new. This CropX, as I said, it's just a couple years old. The Ization probe, I think, is 3 years old. So they're just starting to say, okay, how can these things be used and useful? And I say that because hopefully with Mary's presentation and with this, you realize how important knowing your soil water status is. It's very important information for irrigation scheduling, avoiding some of those problems with tuber malformations, obtaining the best yields, but previous to these newer probes, they haven't made it easy. And that's why that earlier graph when I showed you Washington State, very few irrigators use soil water probes for irrigation scheduling, just because they haven't quite thought of the end user. They've concentrated on the technology, the accuracy, all of that, rather than the utility of them. How can I use them? How can you make them easy for me to use, to incorporate into my production methods type of thing. So the future for soil water sensing and irrigation scheduling, Some other companies are starting to spend the effort in development of interfaces, just like the two I just showed you. So as more options become available, as that's starting to be demanded by the irrigation producers, or just even that very minimal uptake of soil water sensors, then they're going to start asking, well, why is that? And then they will start trying to put that interface more for the final user. And the other thing I say is if the irrigation equipment suppliers, they've got all of the pivot control technology, all on the smartphones and that, Zamatic, Valley, Ranke, they all have a T&L. So if they can start incorporating the soil water sensors with their pivot control technology, with the appropriate display, adequate interpretation, kind of the where am I at as percent available, then I'm pretty sure there will be wider acceptance within the irrigation community for incorporating soil water sensors into their irrigation management regime. Okay? And that's all I have. Thank you very much.
Okay, thank you, Ted and Mary. Again, it was a great job by both our speakers, and there was a lot of information in both presentations. So don't forget that this webinar will be available on our website, spudsmart.com, later this afternoon. If you have any questions for Ted and Mary, now's the time to type them into the chat box. We have about 15 minutes to go over some questions. I have one now for Ted, since it's top of mind. So Ted, what if a fellow, somebody who's listening today wants to go and monitor his soil with a monitor? So give me an example of how he would do that. He has one sensor, so does he walk through the field every 10 feet, he checks the sensor, or does he just do one part of the field? What can he do to adequately monitor?
Yeah, unfortunately there isn't very many probes, soil water probes, that push into the soil very far. So there are some. There's, they might have it's not quite like a hay probe where you put it into a bale and you get a reading once you're pushing it into the soil. So a lot of the probes, if you want to get your soil water status down to anything other than a few, like a foot or so, then typically what they do is they have to install access tubes, and then they will lower the probe into the access tube. So that's typically how it works. So by using these soil water sensors, there are a few that if you just need very, within the top a foot or so or less than a foot, there are some that will push into the ground and you can take a reading. And yeah, you can walk along, push it into the ground, take a reading. But anything further than that, then you have to somehow, install some of these access tubes and then lower the probe into that.
Yeah, and that was, I guess my question is more of how do you monitor the whole field? I'm not talking about depth now. I'm talking about area. So, they're expensive.
Typically, if you have if you don't have variable rate irrigation, when that pivot goes around, the pivot goes around, and it kind of applies the same amount to the whole field. And so what I recommend to most irrigators is I say pick a representative area of the field, not the lowest area, not the hill, but just a representative area where if you went out with your probe, your Camp auger or your oak field sampler or something, and that's where you would determine whether I should start that pivot up or not. That's what I say. Just put one site where you would be making the irrigation decisions. So unless, as I said, unless you have variable rate irrigation where you want to somehow monitor, irrigate that field differentially, then just pick one site, use that as your representative site, and base your irrigation decisions on that one site. If you have varying soil texture, like some fields have two different soil textures, so they'll have sandy loam on half of it if you're lucky, and a clay loam on the other, well then you'd set up two sites for that type of thing.
Right, great. Okay, Mary, it appears that you can't have too little or too much water. So short of raining in Mother Nature, how can growers best manage the moisture in their potato operations? Now, I know that's a broad question, so perhaps in just 3 to 5 main points.
Can I answer with luck?
Yeah.
And it all depends on the area. Some regions struggle more with heavier soil, and therefore have rain events are incredibly detrimental. And that's been my experience up in Manitoba, that there is part of Manitoba that has heavy soil. So it's they irrigate less than, say, in the Wisconsin area where we have sandier soil, but they also use additional management in terms of drain tile. So there are options to try to mitigate the impacts of Mother Nature, and drain tile is the big one. The other thing for me, I personally am a big proponent of a combination of both hand feel and walking your fields and knowing your fields, but also relying on some technology to give you those numbers to make better decisions for irrigation management. So being proactive, both in managing the soil environment with things like drain tile, having good organic matter, for example, in sandy soil, using practices like in-row cropping, cover crops, et cetera, to increase the organic matter in sandier soils that have low organic matter to begin with and low water holding capacities, and then things like drain tile in heavier soils that have problems with water retention. So it really depends on what kind of soil you're dealing with. But some of it, Mother Nature sometimes can make it tough. So sometimes it's just luck of the draw.
Yes. Ted, I know that you had done a 3-year study on water saving using, I guess, furrows, flattening out the hill. Can you explain a little bit about that?
Yeah, we did a bed planted trial because, well, it started out, we just wanted to know the distribution of, what does water look like in an irrigated field? Because typically in southern Alberta, we're a semi-arid prairie and, kind of like the Idaho, and so you don't typically grow potatoes unless you have irrigation. And so ours isn't normally like Manitoba or eastern U.S. where too much water might be a problem. Ours is that, you have to irrigate efficiently to get your maximum yield. So anyway, we looked at what the distribution of water was under, with a typical hill furrow design. And then along with my colleague, Michelle Conchu, we then flattened off the hills and said, okay, if we're, rather than, and that was quite kind of interesting because a fellow in Prince Edward Island had indicated to me, well, we make that design because we're trying to shed water. We're trying to get it off the hill and into the furrow and then down and out of the field, or off the field. But we kind of adopted that hill furrow design and said, well, we're trying to get water into that hill. So to try and get water into that hill, you have to, rather than a peaked hill, we wanted to flatten it off. So we flattened that hill, first of all, just changed the shape of it a little bit so it has a flat top, and then we went a bit further, and then we went with a full, what's called a 6-foot bed, and we double planted into it, and then we triple planted into it to see if we, by the 1/3 extra density within a field, how that affected yields and that. And consistently with it, there were varietal differences, just as Mary had indicated in her presentation with Ranger Russets and Shepherdese, but we found consistently over the 3 years a 10% water saving with either the flattened hill or the bed. Yeah.
Okay, great.
Yeah.
Mary, in the case of a wet growing season, so we're not under irrigation, of course many diseases can take hold. How often should a grower scout a field for a sign of disease, and what should he do if he finds it?
That's a great question. Myself, practices to scout all year long, and you're always looking for different diseases or disorders depending on the time of the year that they tend to show up. But my background actually tends to be storage management. So I personally am most concerned when you start getting 6 weeks, 8 weeks before harvest when you're going to be loading into storage, because those are the problems that are going to be the next problems you're dealing with for 9 months while the potatoes are in a storage building. And I would say, depending on the size of your farm and how many acres you're trying to manage, at least every 2 weeks, having somebody go out and do a really thorough scouting of your problem areas, starting to flag off low spots. If you have a section of a field that got waterlogged and had those open lenticels for 4 or 5 days before harvest, or 4 or 5 days, say a week or two before you were going into harvest, take that portion of the field and either decide to send it directly to your end user or decide to put it on the end of a storage building. But for me, as a storage manager, active scouting is most important, that 6 to 8 weeks before harvest, so you can make those good storage management decisions.
Okay. One question for Ted. So there was lots of soil sensors that you had named in your presentation. Where can a person get them? Where can you get them, and what are the costs? Just the low range, high range?
I did a 3-year study on them, and my criterion at that time was just it had to be below $1,000. So there were some available. Most of them are through Scientific. So in the U.S. too, you have Campbell Scientific, and they have different sensors, TDR sensors, Dynamax in the U.S., Delta T devices in the U.K., all different ones. I guess probably, can you go to your, I guess the question is, can I go to my irrigation equipment supplier and say I want to buy a probe, and would they know these? Probably not, no. But yeah, they're, and that's a good question, Janet, because I don't know, without, they would probably most of the times be directed to your local irrigation specialist or something within the state or the province, and then they could have a discussion on how you wanted to use it, what you want to do with it, that type of thing. But
sure,
yeah,
and I guess
go ahead.
I guess if you just Google in soil water monitors or sensors, you'd find all sorts of options.
Yeah, and as hopefully I've emphasized in that, when you get them, it's not quite the same. So sometimes I've used the example of a hay probe, and it's fairly consistent. When you poke it into the bale, you know what you're looking for to say, yep, that's good, or no, that's too wet, or so you know that. But with soil water probes, there's no number that you can get from these probes that is going to give you any indication on whether you should be irrigating or not without further calculations type of thing. So that's really the struggle I have, and that's really, we've sold them, people have sold them. We had a distributor here in southern Alberta, and when I follow up and say, well, you bought that probe, but yeah, it's someplace in the Quonset, or yeah, I drove over the leads or something like that. So it just was for the information and the time it takes for them to get the information from the previous suite of soil water sensors. Most irrigators, they won't fuss with them. If it's not going to work for them and make their life a little simpler, then they're not. The information is very valuable, but it's just the effort to get that information is not worth it.
Yeah. And Mary, one final question on variable rate irrigation. So that is relatively new. Some are using, some haven't invested in it yet. What are the pros and cons of that, briefly?
Yeah, so variable rate is, like you said, it's a new technology coming out, or a new option, I suppose, for irrigation management. And the question seems to be right now that everybody's asking is, well, is it worth it for me? Is it worth it for a specific field? And how do I figure out if there's enough variability in my field to make it worth it? So we're doing some work here in Wisconsin to help growers answer that question in our Wisconsin setting. The benefits, obviously, are that you are using your water more efficiently based on the soil texture and EC and all those things that you have. It includes some BASF mapping to determine what your management zones are. So, delivering the right amount of water based on the variability in your soil. And anecdotally, I don't have the physical numbers in front of me, but we have seen growers put on a significant reduction in water in areas with, say, a slightly heavier soil texture, and they get the same yield and quality as the other part of the field that has a lighter soil texture that requires more water. So if you can reduce the amount of water that you're putting on, you're reducing your inputs, you're reducing the time it takes to run the pump, et cetera, and you're still maintaining the yield and quality, why wouldn't you want to do it if it pays for itself? And then I've also seen cases where in the process of figuring out if a variable rate system is worth the investment, it includes that Varus mapping. Growers have discovered things about their fields that they didn't necessarily know, or they knew they had a regular low spot, but they didn't understand the extent of that soil type or the extent of that low spot in a field. And they were able to make some management decisions and adjustments based on even just the Varus mapping that was required to install the VRI system. So it's, I think it's something worth looking at. It does not, I don't know that I would say that it pays back in every field situation. So if someone's interested, definitely get with your local irrigation rep and expert and have those conversations, because it's not a solution in every field.
Right. Good information. Okay, everybody. I believe that will be the wrap-up now. We've run out of questions and run out of time. So I want to thank both our speakers for making time in their busy schedules to share their insight and expertise today. I hope everyone's found the information valuable. And again, I would like to thank our sponsors, McCain Foods and BASF, for their support. I also want to thank Kyle Bratolani and Teresa Kurjewicz, our team working behind the scenes, for their assistance in producing this webinar. The presentation will be made available online at SpudSmart, and thank you for your attention. On behalf of the team here at SpudSmart, we hope you have a great rest of your day.